So the next one is not as simple, we must say, because for the first time, our independent variable x appears in the equation. So we have a product x times y. Well, it's important for us to use this method called separation of variables. To this end, it's important that we have sort of a product form of our variables, because otherwise we will be getting problems separating them. So I must be honest and tell you that not every kind of such first order differential equations may be solved with this method. But on the other hand, it's a very, well, simple but important technique which we use all the time, even when solving more complicated differential equations in a later step. Sometimes, okay, you see, after transformation and substitution, and then we find, oh, now it's first order, now we can use separation of variables. So it's used very often. Anyway, what do? We separate the variables. I just take a short form sometimes, right? So what you see is I have already put this in the form of dy over dx. Then I multiplied dx to the other side, and I divided for y or by y. Again, saying that preliminarily this must not be 0 and so on. But also here I get dy over y, which is integrated again to be, you see here, ln modulus of y, and then the right side will be the integral of 2x dx. So that's you can do it in your head, okay, without writing down so much. Well, anyway, the primitive function of 2x, of course, this time is x squared. And then again, this is the usual effect. I explain it once more. We get an additive integration constant on one side. We decide for the x term, usually, where to put it, okay? Then we take away the logarithm by, well, again, applying the exponential. So again, we get our y modulus isolated, now equals exponential of x squared plus c1, the same effect as before. This additive constant in the exponent is transformed to be a constant factor, which is positive, and then taking away the modulus, we get plus or minus positive constant, which is again renamed to be c, element r, without the 0. But in the end, it turns out also here, the 0 function is a solution. So C may be element R, including 0. So you see, it's always the same procedure. And the result this time is C times E power x squared, which is interesting. Please don't make this standard mistakes. I don't know why it happens often. Some people still think that E power x squared may be replaced against E power 2x for some nebulous reasons. It can't be, okay? Because it would mean that x squared is the same as 2x. Why do people do things like that? Well, because most probably they think of the fifth power law, which says that it might be E power x in parentheses, then squared. So actually, this is something very different. And indeed, in this case, it's equal to E power 2x. You see what I mean? If you don't use parentheses, it's always to be interpreted in the form that this one is parenthesed. You know what I mean? And now it's something very different from this. So please remember. Okay. Leave it alone. It's like this is the final result, and that's it. Just let's proceed to the third one right away. Now this time, okay, it looks a little different. It's not a so-called normalized equation because we have some prefactor of the highest derivative inside, but this doesn't really matter. We just add 2y. This time we divide by x. Okay, that's interesting also because now x must not be 0 preliminarily again. We will check afterwards. And then our differential quotient for y prime will be, in the end, it will be 2y over x. We still divide by y and take times dx just to sort our variables, to separate them. So again, we get dy over y here. And here we have 2 over x dx. This is an interesting example for the following reason. actually we have the reciprocal on both sides of the equation. And the only difference, if you compare it, is a factor of 2 on the right-hand side. But now it turns out, importantly, since this kind of equation must always be well integrated to get a logarithm, and then the logarithm must be taken away, the effect will be that such a simple factor on one side of the equation transforms to be a power. Okay, so that's really an important effect you will see shortly. Here, the primitive is ln, again, vertical bars of y. And on the right side, okay, I can just leave this factor alone. It's 2 times ln of, now also here, absolute value of x. And then finally, I have my integration constant. Now, taking away the logarithm, I get my y with vertical bars still on one side. On the other side, I get e to the power of 2 times ln, now still absolute value of x plus c1. You see, this is a little more tricky now to transform, but okay, just remember, we have our logarithm rules, which state, here it is, you know, this is the first one, or is it? I think, no, it's a third one, actually. It states that if you have an exponent inside the argument of a logarithm, you may take this exponent as a factor before the logarithm. Please don't mix this up with any kind of derivation rule, differentiation rule, you know. It looks similar, but it's something totally different. Now, so we can take this the other way around. We can take this prefactor of 2 as an exponent of x, and that's in this case, this is even a certain advantage, because we all know that squaring removes the sign. It removes the signature, you know? So even if x were negative inside these bars, the squaring would take away the sign, so we can replace x absolute value squared against x squared, which is much nicer. So there's nothing negative anymore inside here, you see? Also, here it's positive due to the vertical bars, but we don't need the vertical bars anymore if we take this form. Okay, and then also we have this product form of times e power c1, which is positive, same procedure as every time. Okay, so we get our plus or minus c2 renamed to be c element r. Now, never forget checking c equals 0 allowed, yes or no. In most cases, the answer is yes. So why is it? Because the 0 function, again, is a valid solution. But don't forget, this time we had to say that also x must not be equal to 0. But now in the end, this is much as harmless as to ask whether y may be 0. Why? Well, just test it. If we take the 0 function as a solution, and even if we take any other of these solutions, look at this. This is just a regular quadratic function. It's graphically speaking, it's a parabola, which has its, as you all know, its lowest value in the origin. So it goes through the origin anyway, and the derivative at x equals 0 will be 0. So just inserting here, really in the original ODE, you will find there is no problem, neither with x equals 0 nor with y equals 0 anywhere for y to be the 0 function even. So that's it. In the end, you needn't even discuss this, okay? If you're solving some test exercise in the exam, some exam exercise, you don't have to discuss it. You just write it down and then it's done. So that's it for now. Okay, and let's make a little break.